In this presentation, I will illustrate how the differential of X-ray absorption in matter creates an image. Simply put, why some tissues and organs and foreign bodies show up on radiographs and others not so much. In the past, this was known as subject contrast, but in future, authors may call it signal difference. Before we begin, a note regarding graphics I will use to illustrate my point. To keep things simple, the image receptor graphic will represent the radiation's impact on the final image. We all understand that current digital imaging technology actually measures the radiation dose to the pixels on the imaging plate. To display dose numbers would be impractical, and showing the impact of the final image is much more instructive. Black areas on the imaging plate will represent areas exposed to the primary radiation, with no part of the patient between the tube and the image receptor. These pixels will measure the greatest amount of radiation. Gray areas on the imaging plate represent soft tissues, thin bones, and air-filled organs that partially absorb a portion of the X-ray beam. White areas on the plate will be used to represent bony structures which absorb a significant portion of the X-ray beam and thus measure the least amount of radiation. From a simple standpoint, all X-rays that are directed at a patient can do one of three things. Some X-rays will completely penetrate the patient and go on to interact with the image detector. These rays carry information regarding the shape and composition of a patient's tissues to the image receptor. The likelihood that penetration will happen is governed by the chemical makeup of the tissue and the thickness of the tissue. Some X-rays will be absorbed by the patient's tissues and go no further. The denser or thicker the part, the more likely a given ray will be absorbed in the tissue. Finally, X-rays can interact with the patient's tissues, and the interaction will alter their path of travel. Once the X-ray changes direction, it no longer can be used to outline the tissue or structure that diverted it. These X-rays do not carry information about the patient to the image receptor. They are considered a source of noise or fog to hinder visualization. How is it X-rays can penetrate patients' tissues? To answer this question, we need to shrink down to about the size of a single atom. All matter is made of atoms. The atom is made up of several electrons surrounding a central nucleus. For this exercise, let's imagine the nucleus about the size of a grapefruit. With the grapefruit nucleus, the first electron shell would be about 600 feet from the center. And if you ask about what is in this space, there's nothing in this area of the atom. No air, no matter literally exists inside this space. To carry this example further, let's go out to the next shell. The L shell is about 1,560 feet from the center, more than twice the distance of the first shell. Again, what is in this space? And the answer again is nothing. You can carry this example to the outer shells, and the inevitable conclusion is that the atoms, on a volume basis, is made mostly nothing. Since patients are made of atoms, and atoms are mostly made of nothing, tissues have a great amount of space that X-rays can use to miss the atoms. With that said, modern physics does not agree with this interpretation of the atom. Electrons are not arranged in neat orbitals, but rather in clouds that surround the nucleus with different shapes, depending upon the electron's energy. So why do X-rays penetrate matter? It is probably due to the X-rays' high energy coupled to their frequency and wavelength characteristics. If you think this is not a satisfying answer, I've yet to find a better one, and one that is understandable. When asked, most people will answer the question, "What are you mostly made of?" And the answer I normally get is, "With water." Is nothing. There is a great amount of room for X-rays to penetrate your patients, and they encounter nothing on their travels. Probably one of the biggest influencers of whether X-rays are absorbed or penetrate a given tissue is the average atomic number of that tissue. The atomic number influences the number of electrons surrounding a given atom, and the X-rays that interact with tissues generally collide with these orbital electrons. The one thing we know, the more electrons orbiting the nucleus, the more likely the X-ray photon will interact with that atom. Fat, muscles, and connective tissues are primarily made of hydrogen, carbon, oxygen atoms. A weighted average of the atomic number of soft tissues is about 7. The other hand is primarily made of calcium, which has an atomic number of 20. Bone does not consist of a solid mass of calcium, but rather as a calcium matrix containing fluid-filled channels and reticulations. Taking this into consideration, bone's average atomic number is about 14, approximately twice as dense as soft tissue. The likelihood of interaction is not a simple 1-to-1 ratio with the atomic number, but is equivalent to the atomic number taken to the third power. So, if bone has an atomic number twice that of soft tissue, it has 8 times more likelihood of absorbing radiation compared to soft tissue. Simply put, bone absorbs a great amount more radiation than soft tissue. Here we have a typical X-ray setup with a tube above, image receptor below, and the cross-sectional representation of the forearm in the middle. The white structures in the middle are bone, and the surrounding brown and gray are soft tissues and skin. Bone is considered a positive absorber because it absorbs more radiation than its surroundings. A cone of radiation is emitted by the X-ray tube, and until it reaches the patient is uniform in its intensity. Some of the X-rays spill over the margins of the part and travel unencumbered to the image receptor. This area displays as black on the final image because here the largest amount of radiation reaches the imaging plate. Next, examine the radiation penetrating soft tissues. Soft tissues absorb a moderate number of X-rays and will stop a moderate amount of radiation. The image recorded will appear as various shades of gray. There's not enough density difference in the various soft tissues to project any obvious structures. Soft tissues are better imaged using MRI or CT technologies. Finally, the bone absorbs a large amount of radiation, so the shadow they cast on the final image is white or very light gray. This represents the least amount of radiation reaching the image receptor. Most radiation reaching the imaging plate is in the areas not covered by the patient, and the least are the areas shadowed by thicker bone. Some structures are visible on radiographs because they absorb significantly less radiation than surrounding tissues. These are called negative absorbers. This is especially true for the lungs and gas in the bowel, just to name a few. Here we have a typical AP chest radiograph, and the chest is shown in a cross-section. The large gray structures on either side of the chest are the lungs, and the organs in the middle are the mediastinal structures, the heart, great vessels, and spine. As before, a cone of radiation is emitted from the tube. And like before, some of the radiation spills over the sides of the patient, framing the chest with the largest amount of radiation, which will be black on the final image. Next, examine the area under the lungs. Lungs are filled with air and don't stop much radiation, and are represented by darker gray images. The soft tissue outside the lungs is not as thick as the tissue in the center of the chest, and so will cast a gray image on the receptor. Finally, the mediastinum is a thicker mass of soft tissue in the center of the chest, and a moderate amount of radiation reaches the receptor, so will be represented by a light gray shadow. The spine is recorded as white because it is thicker bone, and the ribs are a lighter gray because they are thinner bones. In this example, the item demonstrated is seen because it has an atomic number less than surrounding tissues. Most radiation is seen in the areas not covered by patient tissues, and the least is the thick soft tissues in the center of the patient. So let's boil this down into a few salient statements. The denser, higher the average atomic number of a tissue, the less radiation will penetrate it. The thicker a structure, the less radiation will penetrate it. Displays, the more radiation striking an imaging plate, the darker this area will be represented on the final image. This convention is a consequence of film screen radiography, where that was the way X-ray film reacted to an X-ray exposure. In the digital era, image densities can be reversed or even have colors mapped upon the densities at the touch of a control or the selection from a menu. Still, most radiology departments conform to the black and white images, where more radiation equals darker images convention is observed. Thank you for your kind attention. Goodbye.